we may not be as intellectually advanced as we like to believe. The powerful space telescopes we have developed, particularly the James Webb Space Telescope, JWST, have captured astonishing images that challenge our fundamental understanding of the cosmos. These observations suggest that the origins of the universe might be even more enigmatic than previously thought, raising profound questions about what events, if any, preceded the Big Bang itself. For decades, scientists have worked under the assumption that the Big Bang was the singular beginning of time and space, an explosive event roughly 13.8 billion years ago from which everything we observe today emerged. However, new data from JWST and other sources hint at a much deeper, more complicated narrative. Before the Big Bang, the universe is believed to have undergone a period known as cosmic inflation, a mind-boggling phase of rapid expansion during which it grew at least 80 times its original size in less than a fraction of a second. This sudden exponential growth transformed the cosmos from an unimaginably tiny point into an enormous expanse that would eventually cool and develop into the universe we know today. During inflation, the universe was cold and sterile, and the vacuum energy that fueled this extraordinary expansion converted into matter and radiation, marking the beginning of the hot dense era that we call the Big Bang. It was during this phase that the fundamental building blocks of the universe, galaxies, stars, and planets, began to take shape. The James Webb Space Telescope, designed to peer deeper into the distant past than any telescope before it, has made discoveries that complicate this conventional understanding. For centuries, theoretical models have held that the universe did not exist before the Big Bang and that the Big Bang was a singular event originating from a specific point in space. New observations, however, suggest a more intricate reality. Instead of the Big Bang occurring at a single location, scientists now theorize that the universe emerged and expanded simultaneously in all directions, creating the very fabric of spacetime itself, rather than expanding into a pre-existing void. An analogy often used to visualize this concept is to imagine the universe as a rising loaf of bread where the raisins represent galaxies moving away from each other. Unlike a loaf with a defined edge, the universe has no discernible boundary, making its true nature even harder to grasp. During the inflationary period, the vacuum contained energy that increased in proportion to its volume, somewhat like an investment that doubles or triples in value over time. This energy eventually dissipated, leading to the creation of matter and the extreme heat characteristic of the Big Bang. Some cosmologists now propose that this inflationary vacuum was essentially infinite and that our universe is just one of many bubble universes in a vast multiverse, a hypothesis supported by quantum theory, which allows for phenomena to emerge seemingly out of nowhere. This idea challenges the simplistic Big Bang model and expands our conception of reality to include an infinite number of universes with potentially different physical laws and histories. Despite the wide acceptance of the Big Bang theory, it still has significant limitations and unresolved questions. While the theory accurately describes a universe that began hot and dense and has been expanding ever since, many details about how exactly this process started remain elusive. Over the years, cosmologists have had to refine and adjust the model to accommodate new observations that don't fit neatly within the original framework. For example, the Big Bang theory originally held that the expansion of galaxies would be governed solely by gravitational attraction, suggesting a slowing expansion over time. Yet, in 1998, astronomers discovered that the universe's expansion is actually accelerating, a startling revelation that introduced the concept of dark energy, a mysterious and unseen force thought to fill the cosmos and exert a repulsive gravitational effect, pushing galaxies apart. Another puzzle concerns the surprising uniformity of the universe's temperature across vast distances. Observations reveal that regions of the cosmos millions or even billions of light-years apart have nearly identical temperatures, a phenomenon difficult to explain without invoking the theory of inflation. Inflationary theory proposes that the universe underwent an extraordinarily rapid expansion during its first moments, smoothing out temperature differences and setting the stage for the large-scale structure we observe today. Since its launch on Christmas Day in 2021, the James Webb Space Telescope has been pivotal in shedding light on these mysteries. Its primary mission is to detect the faint light from the earliest stars and galaxies formed shortly after the Big Bang, effectively allowing scientists to peer back in time. Developed over 25 years and regarded as the successor to the Hubble Space Telescope, JWST is 100 times more powerful. Since becoming operational, it has exceeded expectations, capturing breathtaking images of galaxies that formed just a few 100 million years after the Big Bang and even observing moments before the birth of the first stars. One of JWST's most remarkable achievements is its first direct image of an exoplanet, a planet orbiting a star outside our solar system. The telescope has also photographed the Tarantula Nebula, a massive star-forming region rich in young stars previously invisible to human eyes, and has revealed hidden structures and intricate details within enormous gas clouds such as the iconic pillars of creation. More recently, JWST produced a stunning image of NGC 346, a part of the Small Magellanic Cloud, a dwarf galaxy approximately 200,000 light-years from Earth. NGC 346 is a stellar nursery offering a rare glimpse into a period known as cosmic noon, when stars were forming at an accelerated rate across the universe. Scientists previously believed that star-forming regions like NGC 346 were largely devoid of dust. But JWST scans have revealed massive clouds of dust that actually accelerate star formation. According to lead scientist Margaret Meixner, NGC 346 is the only major cluster in its galaxy actively generating new stars today. This discovery supports the hypothesis that galaxies during cosmic noon were dust-covered, offering a unique window into the early universe. Even more astonishing is the possibility that NGC 346 isn't just forming stars, but also planets. The swirling metallic dust within the region could be the foundation for planet formation, challenging previous assumptions about when Earth-like planets first appeared in cosmic history. This finding suggests that rocky planets could have formed much earlier than astronomers once thought. JWST's discoveries are revolutionary, especially considering it has been operational for just over a year. Despite the complexity of the telescope and the challenges involved in its deployment, it has already surpassed expectations, delivering stunning cosmic vistas that reveal new insights about the infancy of the universe. Besides offering unprecedented views of distant galaxies, JWST has also made surprising discoveries about the existence of 6 enormous galaxies that existed between 500 million and 700 million years after the Big Bang. These galaxies appear far larger and more developed than expected at such an early stage, forcing cosmologists to reconsider their models of galaxy formation and evolution. Some researchers even speculate that what JWST observes may not be galaxies at all, but hidden supermassive black holes, complicating our understanding of cosmic evolution even further. There are various possible explanations for these observations. One is that the methods of star formation were far more efficient than previously believed, leading to the rapid development of massive galaxies. Another possibility is that JWST might be misinterpreting the age of observed stars, making them appear older than they actually are. Regardless of the exact interpretation, the discoveries made by JWST add new layers of complexity to our understanding of the cosmos, challenging long-held assumptions about the origins of galaxies, stars, and planetary systems. Its ability to detect infrared light, which is invisible to the human eye, allows the telescope to peer deeply into the past, capturing the faint glow of ancient stars and galaxies formed up to 13.5 billion years ago. In this way, JWST acts like a time machine, enabling scientists to witness the early universe and its formative processes in unprecedented detail. Although the exact nature of some of the objects observed remains uncertain, the telescope has undeniably revolutionized our understanding of the universe. The discoveries made within such a short operational period hint at even greater revelations to come as scientists continue analyzing its data. These findings may ultimately shed light on some of the deepest cosmic mysteries, including the fundamental nature of the cosmos, the origins of galaxies, and perhaps even the events that preceded the Big Bang itself. Every new image JWST captures serves as a reminder that our knowledge of the universe is still in its infancy. The breathtaking vistas it provides challenge long-standing theories about galaxy formation, the early universe, and the very fabric of space-time. By detecting faint infrared light, JWST reveals galaxies far larger and more developed than anticipated, suggesting that the universe evolved faster in its early years than previously believed. Additionally, the detection of dust-rich star-forming regions implies that planetary systems, including Earth-like planets, could have formed much earlier than assumed. The presence of massive ancient galaxies also hints at the possible existence of hidden supermassive black holes, adding another layer of complexity to cosmic evolution. Though JWST has only just begun its mission, its groundbreaking results promise to transform astronomy and cosmology for decades to come. As it continues to explore the cosmos, it is certain to reveal astonishing details about the universe's past and perhaps even illuminate the profound mystery of what existed before the Big Bang. With each new discovery, we are reminded that the cosmos holds secrets far beyond our current comprehension, urging humanity to continue exploring with wonder and humility. The revelations brought by the James Webb Space Telescope have profoundly expanded our cosmic perspective, demonstrating that the universe is far stranger and more intricate than previously imagined. By peering back billions of years in time, JWST is not only illuminating the birth of the earliest stars and galaxies, but also challenging the foundational frameworks upon which modern cosmology rests. These discoveries compel us to rethink the processes that govern the universe's formation and evolution, revealing a dynamic and rapidly evolving cosmos, teeming with surprises. One of the most striking implications of JWST's observations is the suggestion that galaxy formation occurred far earlier and more rapidly than conventional models predicted. This accelerated timeline implies that the mechanisms driving star birth and galactic assembly were more efficient or possibly different than previously understood. Such efficiency might stem from the dense clouds of dust and gas detected within star-forming regions like NGC 346. These dusty environments, once thought to inhibit star formation, instead appear to foster it, acting as cosmic nurseries where both stars and planets can form in relative abundance. This insight into early planet formation also raises fascinating questions about the potential for life elsewhere in the universe. If rocky Earth-like planets could emerge within these early galaxies, it expands the window for when life might have had the chance to develop, inviting speculation that some of these ancient worlds, perhaps billions of years older than Earth, could have hosted or even still harbor life forms, offering a humbling reminder of our place in the vast timeline of cosmic history. JWST's detection of unexpectedly massive galaxies so soon after the Big Bang suggests that some of the earliest cosmic structures were far more mature and complex than once believed. This observation raises the possibility that supermassive black holes, whose origins remain one of astrophysics' greatest enigmas, might have formed rapidly and played a key role in shaping these early galaxies. Understanding how these colossal entities came to be so early in the universe challenges existing theoretical frameworks and calls for new physics or astrophysical processes to be explored. Furthermore, JWST's ability to observe the universe's infancy also touches upon deeply philosophical questions about the nature of reality and the origins of everything. The concept that our universe might be just one bubble among an infinite multiverse pushes the boundaries of human comprehension, forcing us to ask why our particular universe has the physical laws it does, and what conditions might exist beyond our cosmic horizon. This multiverse hypothesis, while still speculative, is gaining traction partly because of observations that suggest our universe's beginnings might be part of a much larger and more complex structure. At the same time, the accelerating expansion of the universe, attributed to dark energy, remains one of the greatest mysteries in physics. JWST's insights into the early universe may help unravel the properties and origins of this mysterious force. Dark energy's role in pushing galaxies apart faster over time influences the ultimate fate of the cosmos and shapes its large-scale structure in ways we are only beginning to grasp. Despite these profound scientific advancements,